All right, so let's get started. I'm really excited to introduce Kevin Dykema. Kevin's from Mattawan, Michigan, where he teaches middle school math. He's been doing that for, I think, about 26 years or so, or oh,
You
pretty
got it.
long time, pretty long time. He's also done a lot of professional learning consulting, delivering professional development. I'm going to tell you that his passion for mathematics education is infectious. So this is going to be a lot of fun tonight. He is co-author of The Productive Math Struggle that was published in 2020. And I think this is a first that the three folks on here tonight are all Facebook friends. So Ryan, Kevin, and myself. I don't know if that's ever happened before, but but tonight, mark your calendars, right? Or go buy a lotto ticket, however you want to celebrate. And as you heard earlier, Kevin was officially welcomed as NCTM president on October 1st. So just 11 days ago. And we are proud and pleased to have Kevin with us this evening. So Kevin, I am going to get out of your way and let you have some fun.
All right. Thanks, Mark, and welcome, everybody. I'm very excited to be with you here this evening, this morning, this afternoon, depending on what time zone you are in, or if you're watching the recording or not. So as Mark said, I am the current president for NCTM. And before we dive into that, I just want to say thanks. Thanks for giving up an hour of your time to grow professionally and to think with me about how can we better meet the needs of each and every one of our students. So as Mark shared, I'm the current president for the National Council of Teachers of Mathematics. Some of you may be familiar with it. Some of you may not. There's our mission statement. There's what we do. And the words that always jump out at me is that each and every student. We're always looking for ways that we can help meet the needs of every single one of our students. And I look at using manipulatives as a way that helps meet the needs of some of our students. So I think about NCTM, one of the more visible things that we have are some conferences. So if you want to come join me in Baltimore at the end of November, come join me. It'd be great to see you there. If you're more of a virtual person, NCTM has a virtual conference at the end of March. Or come join me next October, a little over a year from now, in Washington, D.C. for our annual conference. Now you may be saying, hey, I don't have money to be able to attend some of these. Great news. There's a website you see there, that nctm.org/grants awards. We have a mathematics education trust. And as part of that, we give away lots of money. And I've been told that some of the different awards are not highly competitive, that some years only 2 people apply or 3 people apply. So be that 4th person. Your odds are good for some of those. And you can go to the website and you can see all the different things, but they're good for things like coursework, for professional development, conference attendees, getting materials in your classroom. And then finally, I'm all about saving you money. So if you are a member and when you renew, you can use this code. If you're not a member of NCTM and you're saying, hey, I want to join, there's a code you can use, that board23, and that'll save you a little bit of money. But let's dive in to the purpose for our time here this evening. So you see an ancient saying there that I absolutely love. I'll confess, I did very little doing in my K-12. I'd also argue I did very little understanding of the math. I was a great rule memorizer. But get me to explain why something's happening, see those connections, couldn't do that. And I was a straight A minus, throwing a B plus every now and then if I was having a bad day student. It wasn't until I started teaching that I finally started getting to that understanding stage. And I started to see some of those connections. I don't want my students to have that same experience. I want my students to get to that understanding stage. And that means we got to do it a little bit differently to get them to that point. There's also a definition of insanity that I love to talk here. I think our middle school, as I sort of scrolled through, being a middle school teacher does not make you insane. Although if you taught for a long time, you may have to be a little mentally insane to truly enjoy them. And, you know, my wife likes to remind me sometimes I'm not an 8th grader and I can act like an adult when I'm home. And I always appreciate that gentle reminder. But there's a definition of saying that I like to talk about. We can all think of a colleague, none of us here on this webinar, of course, that when they reteach something, they say the same thing, just slower and maybe a little louder. I want to look at some ways that we can use some manipulatives, get our students actively engaged, get them thinking about the math, get them starting to make some sense of what's going on. So I want you to find that chat box again. Make sure you've got the chat box set so that it's displaying to everybody, and then type in the first 3 words that you think of when you hear the word struggle. So find that chat box, change it, throw in 3 words. You could throw in 1 word, 2 words, 4 words. It's not a pop quiz or anything. So I see a lot of difficult, frustrating. I see some fun, tough, hard, pain, giving up, problems. I give up, absolutely, difficult, tiring, stuck, frustrating, perseverance, good, not yet, lack of understanding. So as they continue to scroll through there and keep coming in there, notice that for many of us, the words that we initially associate with struggle are negative in connotation. That many people view struggle as a bad thing. And I want to argue that struggle is a necessary part of learning. And we'll talk about what that means in just a minute, but I want to step out of the education world for a brief moment. Think about learning to ride a bike. There's definitely struggle involved with learning to ride a bike. And yet we value that struggle. We recognize it's through that struggle that true learning occurs. In fact, we value it so much, we give it a scaffold. Now, we don't call it a scaffold, we call it training wheels. Our ultimate goal is that we learn to ride the bike without those training wheels. In many respects, I think of using manipulatives a little bit like training wheels. We don't want to do the math with the manipulatives. We want to learn that math with those manipulatives. Just like we don't want to ride the bike, we want to learn to ride that bike. I want to learn that math through using manipulatives. I also think about swimming. There's a lot of struggle involved with swimming, and we value that struggle as a society. We recognize it's through that struggle that true learning occurs. And I'm always struck by the role of that swim instructor. That swim instructor is not doing all the work. It's not like the swim instructor is grabbing the child's arms and propelling them through the water, grabbing the legs and kicking them. No. The swim instructor is there saying, you're not going to die. You know what to do. I believe in you. Remember, here's what you need to do next. And I wonder how often I am not like that swim instructor. I wonder how often I'm doing all of the work in my classroom and my students are along for a free ride. So whether we're learning a new dance move, learning a new sport, learning a new song, learning to drive, learning to ride a bike, we value that struggle in society. We need to have that same sense of appreciation as we're learning math. Now, I'm not advocating for, I see kids who have no idea what's going on. Yay! No, I want them to wrestle through with that. So when I think about, what do I mean by this notion of productive math struggle? You see a quote right there. It's one of my favorite quotes from the book. I think students have to have that first crack at making their own meaning. In way too many classrooms, mine included at times, unfortunately, the teacher stands in the front and says, here's what you need to do, and the kids just try to memorize that. So much better stuff happens when we allow our students that flexibility, that opportunity to start to try to make some sense of their own understanding. So I want to spend some time and just look at a variety of different middle school type of topics. If you're not a middle school teacher, you can apply the different ideas to different grade levels, but it starts to give you a sense of the power and what students can gain from that. So we're going to start with some color tiles. And I'm going to switch to Brainingcamp, and I want to go to my color tiles here a minute. You can follow along, you can watch. If you're going to go to Brainingcamp and you've got side-by-side screens and you want to play with it, that's great. If you want to draw a picture of it, that's great. If you want to just think about it, that's great as well. So many different options with that. So here's what I want you to do first. I want you either to build, think about how it's going to look, draw a quick little sketch. I want you to build a rectangle that's 2 by 3. So build a rectangle, please. That's 2 by 3. And I'm going to give you just a brief moment for it, not very long. So I often see when I'm in a spot where I can easily see everybody's, and I chose not to do this one as a live one. We'll do a live at the very end, and you'll see that feature. But I often see answers that look like these two. Some of us have it more horizontally aligned. Some of us have it more vertically aligned. If you have it more horizontally aligned, you use 6 color tiles. If you had it more vertically aligned, you also use 6 color tiles. Some people get all hung up that one of those is definitely 2 times 3, one of those is definitely 3 times 2, and that may have an important factor for some uses. But when I'm first introducing some of this stuff, I tell my students, all right, we're going to call both of these a 2 by 3 because we're getting the same thing either way. Congratulations, you've discovered the commutative property of multiplication. They're always less than thrilled with that name. I'm going to switch it up here now, though. So this first time I gave you the dimensions, you had to figure out how many color tiles you would use. Now I'm going to switch it and say, all right, count out 8 color tiles. And I want you to make all of the different size rectangles that you can using all 8 rectangles or all 8 color tiles. So I don't want a rectangle of 5 and a rectangle of 3. I want all of the rectangles to have 8. So I'm going to give you a brief moment to figure out what are the possibilities for a rectangle of 8. Now my class is way longer than what I'm giving you here. But you should have been able to find a 1 by 8 rectangle and a 2 by 4 rectangle. I may do the same thing with some other numbers. I may say, all right, you find all of them, then that'll make a rectangle with 12. I happen to know a 1 by 12, 2 by 6, 3 by 4. Maybe I give them 9. They find the different ones, 3 by 3 and a 1 by 9. Maybe I give them 7. They find a 1 by 7. Maybe I give them 10. They find a 1 by 10, 2 by 5. Put your teacher hat on now. What are we really finding of 8, 12, 9, 7, and 10? We're really finding those factors. A very important topic in the middle grades, and we do a lot of work with developing that. But this is not how I learned about factors. I just learned factors as those are the numbers that evenly divide into a given number, and it didn't make sense. We just practiced it over and over and over, and it started to make a little bit of sense to some of us. But here, I can make what can be a very abstract concept very, very concrete. And I can have students who are thinking of factors as doesn't make a rectangle, does it not? I could also open up that conversation and then say, all right, hey, some of these have multiple rectangles. Some of them only have 1 rectangle. I didn't choose another one that only has 1 rectangle. We could introduce that vocabulary prime and then composite. So many different ways that we can take using those color tiles. I can have them draw sketches of it, but there's something about giving those kids the color tiles, whether you do it with the physical manipulative, whether you use it with the digital version of the manipulatives. Absolutely, Carol, and all you are half a step ahead of me there with the prime versus composite. So there's one use of my color tiles. I want to switch in and do another use of them. And this one I went ahead and put as a code. So I think Mark is going to share the code in there. And if not, I'll share it and we'll be good from there. So I know that in the middle school, we do a lot of work with finding patterns, describing different patterns. So I pre-made one of those patterns there. So Mark did put that code in there. Remember, if you want to get the code, to go back to your regular old Brainingcamp screen, it'll say a share code. If you type in that code that Mark shared, it'll make your screen look like mine initially. Once I start writing, you won't see that writing on there. But I know that one of the things that we need to work with is finding patterns. And this applies to elementary grades, it applies to middle grades, it applies to high school grades, depending on the language that we use with that. So I've given the start of a pattern. I usually have my students look and say, all right, we had started with a 1 by 1 square. To get the next biggest size square, we needed to use 3 color tiles. The second picture, we start with a 2x2 square. We need to add 1, 2, 3, 4, 5 to get the next biggest size square. Then I may have them fill in that next row. Sometimes I just give them the first pattern and describe it verbally. Sometimes I give them the first 2 pictures. Sometimes I give them all 3 pictures. Lots of options to do there. And then I like to turn them loose and say, all right, you find for the 4th picture, the 5th picture, the 10th picture, and then the nth picture. Give them a little bit of time. They go through and figure it out. Some of you may figure out the pattern. Hey, if it's 3, 5, 7, I bet it's 9, 11. My middle school students initially jump and say, oh, that's 13, because they just want to go 3, 5, 7, 9, 13, or 11, 13 and call it good. Then they quickly realize, oh, wait a minute. He tricked us a little bit in their language, and he jumped from 5 to 10. The second guess that they'd like to make then, if they don't want to have to do a whole lot of thinking, they just jump and say, oh, there's 22. And I love when that happens, because some of my students are going to say 5 times 2 is 10, 11 times 2 is 22. I could draw that 10 by 10, build that 10 by 10, but oftentimes I just like to go back and say, all right, hey, let's look at 2 and 4. 2 times 2 gave us 4, but 5 times 2 does not give us 10. Bummer. We have a new type of relationship there. So then most of them figure out, all right, 13, 15, 17, 19, 21. They change it to 21 and they're feeling good and they're ready to move on. And then they realize, hey, wait a minute, we still have this nth term. And that first year, very few of them figured out that nth term. And I quickly realized they're just looking at the pattern 3, 5, 7, 9, 11. They're not looking at the relationship between the two. So the next year, instead of going 1, 2, 3, 4, 5, 10, n, I threw in 100. No middle schooler wants to build a 100 by 100 grid and figure out how many are needed for that next one. No middle schooler wants to go 23, 25, 27, 29, 31, 33, 35. It takes too long. They start to look for patterns. They start to recognize, oh, we added 2. I remember from middle school or from elementary school, adding 2 a lot is like multiplying by 2. So they say, let's try 2 times 100. 2 times 1, 2 times 2, 2 times 3, 2 times 4. They recognize we're 1 off every time. So they want to add 1. So they get to that 2 times 100 plus 1. And when we have that 2 times 100 plus 1, I'm golden. Because then it's not as much of a leap to get to that nth term. I may ask, how would you find the 1,000th? How would you find the millionth? How would you find the bazillionth? And just sort of arrive different numbers. And eventually they start to recognize all we need to do is 2n plus 1. Again, not how I learned to write the equation of a table. I was just told, find the slope, here's how you do it. Find the y-intercept, here's how you do it. It was all memorization. And I was just given a sheet of tables and we had to find it all. There was no reason for me to, in my middle school mind, there was no reason to go through and find all of the different equations for those tables. It was a bunch of unnecessary work, in my view, at that point. Here, I've given the students a reason why it may be important and why they may care about it. I want to share one other quick little one with these. And there's a code for this one as well, if you want to see it right in front of you, that Mark will throw in there. This one, the pattern's a little bit different. This one, I started with a 1 by 1 square, completely and totally surrounded it. Not like the prior one where I just wanted to know how many to build the next biggest size. I'm totally surrounding it. It took me 8. Second one, a 2 by 2 square, completely and totally surround it. It takes 12. For the third square, has 16. Did the same thing, asked them for 4, 5, 10, 100, n. I was expecting that they would all give me 4n plus 4. One of the first times that I did this, I had a student raise their hand and say, I didn't get 4n plus 4. I got a different answer. I said, great. Tell me what your answer is and how you got that. I said, I have 4, and then in parentheses, n plus 1. And I'm doing my quick little calculation saying, all right, that is an equivalent one. It's going to work. And then in one of my rare early career great moments, I said, all right, how did you figure out what was 4 times n plus 1? And they said, I didn't really look at the actual table. I just said there's a square, n tiles by n tiles. I knew the top had n tiles plus a corner. The side had n tiles plus a corner. So the 3 plus the corner, 3 plus the corner. The n plus the corner, the n plus the corner. I said, wonderful. And I said, I wonder if there's any other ones that you can come up with. And it gave them a few minutes to try it out. And of course, as we know, they were able to come up with some other options. Just a second here. There we go. I shouldn't be pushing an extra little button on my little stylus there. I apologize for the user error there. Some of mine came up then with 2n plus 2's plus 2n's. When I asked, hey, what did you do there? The full top, full bottom, so the n plus those 2 corners, n plus those 2 corners. Oh, I was right. Plus the n along the side, the n along the other side. Another student raised their hand and said, oh, I did 4 times n plus 2 minus the 4. How'd you get that? Full top, full bottom, full side, had those 4 that were overlapping that I counted twice, and you can subtract off 4. So we had at least 4 different possibilities. They, of course, being the good middle schoolers they are, they all want to know who's right. I said, I'm not sure. So then I had a third of my class simplify that top expression. Another third of the class simplify that second expression. A third of the class simplify that bottom expression. They recognize, oh, they all simplified to 4n plus 4. And all of a sudden they were set. They had a reason of why we'd like to simplify expressions. Why don't we sometimes just leave our answer as 4 times n plus 2 minus 4? And they started to see the reason that we do some of that symbolic manipulation. All from a real worldish type of a thing. You may think, it's kind of a corny little thing, but they were excited. They had a reason to find that nth term. It wasn't something that was just being done to them. So I want to switch gears here. And I want to look at some algebra tiles a moment. I know that one of the topics in the middle grades that so many students struggle with, and actually beyond middle grades as well, is this notion of adding and subtracting integers. If you've never seen algebra tiles before, here's a real quick crash course on them. There's 3 different pieces. There's a positive side for each of them. There's also a negative side for each of them. X squared, x, 1, negative x squared, negative x, and a negative 1. I'm going to clear all that off. And let me change and not have everything labeled on there for just the time being for a moment. So when I want to do integers, I just want the little itty bitty baby pieces. And it's all right, there's our positive 1, there's a negative 1. Maybe I ask my students, all right, you model a positive 3. And they just click 3. Wonderful, all right? You model a negative 2. They're all set. That's all right, here we go. What happens if I have 1 positive and 1 negative? What is that really going to give me? Give the students some time to think. They can relate it to money. I had $1, lost $1. And for most of them, if I keep it with 1 and negative 1, they start to recognize it makes a 0. One of the neat things with a virtual, as you saw, it just disappeared. If the students are using a physical model of it, obviously they're not just going to disappear, but they can slide it in the virtual and it's gone. So I tell them, all right, here's your goal. I want you to model 5 plus negative 2. Represent that with your algebra tiles. And let me just drag those there a minute. So there's 5. They had negative 2. That's all right. Let's find some 0 pairs. Do we have any? Now, for many of us, we can just look and say, oh yeah, clearly we have 3 zero pairs. Not all of my students could just look, or excuse me, 2 zero pairs. Not all of my students can just look and say, oh, there's 2 zero pairs. Some of them, at least initially, need to take them off one at a time. There's a 0 pair. There's a 0 pair. They see 5 plus -2 is 3. Notice, I haven't said, here's how you find here's how you add integers. I want them to start to make that connections. I want them, did I say -3, +3? I don't know what my brain did there for a brief moment. So we start out with 1. And then maybe say, all right, you guys, there was one problem. Let me give you 3 or 4 or 5 that I want you to try. I have to be careful. I can't always make the positive number have a greater absolute value, or they find a pattern that doesn't exist. So I switch things up and make sure I get some that will give a positive answer, some that will give a negative answer. Maybe I even throw 2 negatives in there, a variety of different things. Give them 5-6 minutes. They go through, use their algebra tiles. They're finding all the answers. -3 plus 7 is 4. -3 plus 1. 4 plus -6. -2 plus -3. Usually I give them 8, 9. As I'm walking around, as we do a quick spot check of the answers, they're all excited. They're getting every single problem right. And for many of them, it's the first time that they may be getting a number correct right off the bat, and they're all tremendously excited. But think back to the training wheel stage. This is really at the training wheels. They're really using the algebra tiles to find the answer. I want them to learn with the algebra tiles. I want them to learn with the manipulatives, not do the math with the manipulatives. And I saw that question in the chat box. I'll come back to that question in just a moment. So we have those. I want to take it to that next step then. So tell me, all right, you guys, here's what we're going to do next. Some of you think you may see the pattern. Some of you may not think you found a shortcut yet. If you think you found the shortcut, the way to do it without the manipulatives, don't tell anybody yet. Let somebody else have that opportunity to continue to grapple, to continue to wrestle with it. One of my colleagues sometimes says, don't steal someone else's thinking. Give them that opportunity to think. And that's what I'm thinking about when I talk about, that's what I like to think about when I talk about productive struggle. We need to give our students that time to think, start to make some sense. So tell them, all right, here's what we're going to do next. I want you to draw some pictures. If I have 4 plus -5, we're going to draw a quick picture. We're not going to use our algebra tile. No, we are not going to grab our colored pencils and sharpen and spend 30 minutes sharpening the yellows and the reds. Let's just agree for our +4, we can use 4 positive signs. For our -5, we can use 5 negative signs. Some of my students sort of put a little oval around the positive and negative for the 0 pair. Most of them just like to draw a little line. They got 4 plus -5 is -1. If they did it for -3 plus 5, 3 negatives there, the 5 positives, make those 0 pairs. And all of a sudden I'm starting to hear, oh, and that, you guys, that's my favorite sound in the middle school classroom. When I hear that, oh, I know they're starting to get to that understanding stage. They're starting to make those connections. They're starting to see what to do. So I start out, use the manipulatives. Transition, draw the picture. And then I say, all right, let's go one step further. What would 50 plus -51? How can we figure out that answer without having to draw all 101 of those positive and negative signs? Turn to your neighbor, share an idea, and then they give me the great language. Like, oh, if the signs are different, subtract the number parts, choose the sign of the bigger number part. They don't call it with the absolute value. They have some different language, but they've made that connection. And when they make that connection, when they get to that understanding stage, that's when that true learning is happening. That's when they're learning to ride the bike. That's when they're learning that new dance move. That's when they're learning to drive a car, whatever the case may be. Does this take longer than if I just told them, here's the rules? depending on how you define take longer. If I just tell them the rules, yeah, maybe it takes one class period. But think 3 months down the road, 3 days down the road, perhaps. You give them a refresher. They also, we don't know how to do this. We've never done this. You spend another day reteaching that topic. 6 months later, you spend another day reteaching that same topic of adding positives and negatives. So you may spend in any grade, you may spend at least 3 days just telling them, here are the rules when you try it all by memorization. And you know that we still don't have some of our students. When I give them the time to use the manipulatives, draw a picture, make that nice progression of learning, all of a sudden they get to that point where they understand. It may take me 2 days at the beginning, but then it's 5-minute refresher, 10-minute refresher, and it more than makes up for it. As long as I buy my algebra tiles, there was a question of how could you model a negative, subtract a negative. So I'm going to look at -3 minus a -1 to start out with. So I want to look at -3, subtract a -1. There's our -3. When we added, we put onto our workspace. When we're subtracting, we're going to take off of our workspace. So that -3 minus that -1, I can take that away. We end up getting a -2. For most students, that's not where the tremendously difficult part comes in play. They can do that as long as I keep that larger absolute value first. It gets to be a little bit more exciting if we put the larger absolute value second. Something like -1 subtract -4. There's my -1. I want to take off 4 negatives, but I don't have 4 negatives to take off. So sometimes I tell my students, all right, hey, before we took off some 0 pairs, let's put on some 0 pairs. There's 1 0 pair. Now do I have 4 negatives I can take off? Nope. Let's put on another 0 pair. Now do I have enough to take off? Nope. Now do I have enough to take off? And they realize, oh, now I can take off my 4 negatives, and that gives me a +3. That leaves me a little unsettled because it still feels like they're doing that math with that. When I want to start to help them understand that subtracting of negatives, I like to start with a positive and subtract a negative, something like 2 minus -3. And say, all right, there's our +2. We want to take off 3 negatives. I don't have any negatives to take off, so let me put a 0 pair on. Now I don't have 3 negatives. Let me put another 0 pair. Let me put one more 0 pair on. And I could keep putting on lots and lots of 0 pairs if I really wanted to. And usually then I say, all right, hey, let's take those 3 negatives away now. But before we just count and say there's 5, if I had just given you this picture at the beginning, what math problem would you have told me it was? And they would have said, oh, it was really 2 plus 3. And that leads us into a conversation that when we're subtracting a negative, it's the same thing as adding the opposite. There's lots of other ways that you can do it, but that's the way that I found that's such a powerful thing for so many of our students. So I'm looking at that adding of integers. It gets us to be that nice thing. Oh, and thanks, Ryan, for the reminder that there's a nice little 0 pair counter with the 2 color counters. And the 2 color counters work the same way as the algebra tiles. So many different manipulatives that work so similarly for some things, some little tweaks here or there with some different things. But I want to switch manipulatives here. So we did a little bit with the algebra tiles, a little bit with the color tiles. I want to look at an XY coordinate pegboard. This is one of my favorite manipulatives. And if I haven't said that before with the other manipulatives, they're all my favorites. I don't really have a favorite, but this is one of those, for so often when we get to those middle grades, some of our students are reluctant to want to use a manipulative because they view it as an elementary thing. Oh, that's what I used when I was in elementary school. So I like to find those manipulatives that they may not have used in elementary school. They're probably not using an XY coordinate pegboard in elementary school. Maybe in 5th grade when you start to do a little bit of work with graphing. So here's the first problem I like to give them. I just give them 6 ordered pairs. Now remember, I've taught 8th grade for many years. They should already know how to graph. They've done some work with positives and negatives. So I can do this at the beginning of the year. I want to give them a quick little refresher of that. I could give them a piece of graph paper. I give them a pegboard instead and say, all right, you graph those 6, connect them with a rubber band. So I've got it already done for us to speed things up. There's the shape that it ends up making. You can either use the code that Mark just put in there, or you can just go to the XY coordinate pegboard and you're good there if you want to play along with the rest of us. I could stop right there and say, hey, yours, if yours looks like mine, we're all set. But I want to take it just a half step further. And a lot of times I like to say, all right, what shape is that? Now I'm convinced that students should know the name of that shape. I mean, it's not like 8th grade, middle school is the first time they've learned the shape names. They've worked with those shape names in the elementary grades. But when we think about that geometry strand, it's usually 1 unit at any grade level. So maybe in 3rd grade in February, they do all that work with shape names. They know those shape names down pat. And for many of them, they don't hear those names again until 4th grade February and then 5th grade February. So I look for places where I can just throw in some of those reminders of some of those different words. So we say, oh, yeah, great, it's a hexagon, all right? And then maybe say, hey, let's look at it. This side and this side. If I continue them forever and ever and ever, they're never going to touch. What's that called? Bring up that parallel with that. Oh, what's that point where 2 of our sides touch? What is the big fancy math word for that? And they look and say, I don't know what it's called. Say, sometimes with my quirkiness, say it starts with a ver, ends with a tex, and they're all like, oh, vertex, and I praise and say, hey, you guys must have been a great mind reader at that point in time. But I like to use sometimes that practice of graphing, throw in some of that vocabulary as a quick refresher. So there's one use for the pegboard. There's lots of other things I like to do with the pegboards as well. Oops. Sometimes, let me go back to here and just get a clean one with that. Sometimes I like to, and notice with the pegboard, by the way, the axis, or you can get the axes to slide all around with that if you wanted to. And let me actually, yeah, no, we're gonna leave it as that. There we go. We'll be good with that. Sometimes I say, all right, you graph a line. Now I used to, when I worked on graphing lines and we want to get into the middle grades, I used to just tell them, here's how you find the graph. Take that +1, put a peg there, go up 2, over 1. I just did all of that talking at them. And that was not a very powerful tool for many of them. So now I've switched how I do this. All right, hey, I want you to figure out, what would the graph of y equals 2x plus 1 look like? I believe that you have the ability to figure it out in your group, so I'm just not going to tell you what to do. You spend the time, see if you can figure it out. And then I like to look busy for just a real brief moment there and let the kids get started. I used to go straight to monitoring mode and start walking around the room and working the room. Quickly realized as soon as I started to monitor, they all turn to me and start asking questions. If I give them that opportunity to think first, most of them start out by making a table. That's all right, let's see. If my x is 0, 2 times 0 is 0 plus 1 is 1. 2 times 1 is 2 plus 1. 2 times 2 plus 1. And then they take those pegs and graph them there. 0 with 1, 1 with 3, 2 with 5. Some of them like to connect it with the rubber band. Some of them don't like to connect it with the rubber bands that come with it. Some teachers are fearful of the rubber bands. Here's how I solve that rubber band issue. And in my 26 years of working with 8th graders, I have never had an 8th grader intentionally shoot a rubber band. Maybe you're thinking, how does that work? It has always been an accident. They claim they never intentionally shoot it. They always have claimed that's an accident. So here's what I tell them. If you accidentally shoot your rubber band, no big deal. I'm going to calmly walk over. You're going to give me your pegboard for today. We'll call it good. It's not a lifetime banishment, but we're going to be done with it for right now. So now they can connect it with the rubber band. They cannot connect it with the rubber band, whatever they like. Give them another one. Give them y equals maybe negative 3x plus 5. They make the table, graph those. Get a few more of them. Then we start to get brave and say, all right, let's throw a fraction in there. And I give them a great hint and say, all right, to make it a little bit nicer to graph, whatever your denominator is, use that for the scale on the x's. So 2/3 times 0 is 0 plus 1. 2/3 times 3 is 2 plus 1. 2/3 times 6 is 4 plus the 1. They can take their rubber bands, do all that, or I take all their pegs if they want. 0 with a 1, 3 with a 2. They're golden with that. And then we can start to have a conversation. But how can I actually read my own handwriting? And again, some of them connected with a rubber band. And a lot of times I just draw the line on there if I wanted to draw the line, don't draw the line, whatever the case may be. And then I start saying, all right, let's see if we can find some patterns. Let's see if we can find some shortcuts. Where did that 1 show up in the graph or table? Where did that 5 show up in the graph or table? Where did that 1 show up? And they start to recognize, oh, that's that y-intercept. Where did the 2/3? Where did the negative 3? Where did the 2? And they may have to think of it as 2 over 1 initially. Say, oh, we went up 2 spaces over 1. Here we went up 2 spaces over 3. And all of a sudden I can make that connection to that slope-intercept form. So as an early career teacher, I just started out saying, here's the slope-intercept form. Let's rock and roll with that. Now, whatever stage of my career I'm in, I like to give them the equations and say, you build a table, you figure it out, let's find those shortcuts. Some of my students stick with making a table for the rest of the year. Do I really care? Absolutely not. Because when I think about it, when we get later on and start looking at something like y equals, and let me switch colors here so you can see it a little better. If we look at y equals x squared minus 3, we often tell them at first, build a table. When we look at the absolute value function later on, oftentimes we say, build a table. And for all the non-linear ones, we had them build a table. But so often when we're looking at lines, we jump straight to that slope-intercept form and don't allow them to start to make some sense. All right, so let's try another idea here with that. Oops, I keep forgetting that I can't just do the clear all on there. That is a user error with that. Let me clear those annotations. There we go. All righty. So I apologize for those user errors. I can also use this when I want to start doing some work with the graphing the inequalities. If I want to graph a linear inequality, something like, y is less than 2/3 x plus 1. Some of my students may want to build a table first. Some of my students may be at the point where they say, oh, I know it's going to be starting at the 1, up 2 spaces over 3, up another 2 spaces over 3, maybe up another 2 spaces over 3. And I tell them, all right, here's what we're going to do. If it's going to be a solid line, connect it with a rubber band. If it's not going to be a solid line, don't connect it with a rubber band. So this one's not going to be with a rubber band. And then I tell them, all right, to decide which half plane is going to get shaded, please don't spend an hour putting in 100 pegs and then pulling out 100 pegs later on. Instead, just sort of put one peg over in the corner from where you want, and then let's take a rubber band and we connect from our original line to that peg in the corner, and it starts to look a little bit like it's shaded. It doesn't work perfectly with it. It looks a little different, but it gives them another way to get them actively engaged with that. So I can use my pegboard to have them learn how to graph a line. I can also use the pegboard just as an extra engagement tool to get a little bit of extra practice. And we know they need that extra practice. I can use the pegboard also, when I'm working with coordinate reflections, reflecting over the x-axis, over the y-axis. Maybe have them build a triangle in quadrant 1, reflect it over the y-axis, then go through and add all of those ordered pairs on there. Ask them, hey, what was the relationship you saw? What's sort of the shortcut? I want to look at one last manipulative. And there's so many great ones to use at the middle grades. There's so many great ones to use in high school. There's so many great ones to use in elementary school. Oh, and good thing I put myself a little note there. I also like to use that pegboard when I'm doing the initial graphing the systems of equations. When they try to do it on a piece of graph paper, they don't draw their lines straight enough and they can't find that exact point of intersection. I give it to them and give them with a pegboard. They can find that exact point of intersection. Usually they say, I can't put a peg there because there's already one there. It's like, congratulations, you just found that answer. So I'm gonna look at one last one. And this one we're gonna do as a live, just to demonstrate how to use that live. So let me grab that share from here a second, grab the live. All right, so now we're all set with that live. There's the code that you can put right in there if you want to try right along with me. And let me copy that code, put it in the chat box so I can move that out of the way. Oops. And let me, Mark is probably faster than I am. Has it there? Oh, Ryan's faster than I am. Nice. All right. There's that code. So I use my pegboard, or excuse me, my Geoboard. And sometimes people get the Geoboard and the pegboard confused. The pegboard, notice, has on a physical, has the pegs sticking up. You put rubber bands, or excuse me, that's the Geoboard. The pegboard, you put the pegs in and then connect it with a rubber band. When I'm looking at this Geoboard, the pegs are sort of in there already. We're just gonna wrap some rubber bands around there. So one of the things I like to do is just do some work with vocabulary. There's the 3 little clues. The shape has 4 sides, has only 1 pair of parallel sides, no sides are congruent. So I want to give you a brief minute to see if you can build a shape that fits those 3. Now, if you didn't log into Brainingcamp, not a problem at all. Think about it on a piece of paper, see if you can draw a shape that has 4 sides, only 1 pair of parallel sides, and none of the sides are congruent. So I'm going to give you a brief minute to see what you come up with. Sometimes my students find that drawing goes faster than using the pegboard or using a Geoboard. Sometimes they're more willing to use that Geoboard because if they make a mistake, they can just quickly take their rubber bands out and nobody needs to know that they weren't perfect at any given moment. Listen to that, it's totally great to do it on a piece of paper. I just wanted to show off another feature of Brainingcamp. If you look back at my screen, then down the bottom, you can see some different student responses, and some were able to find it, some weren't able to find it because I didn't give a lot of time with that. But think back to that geometric vocabulary. There's tons of vocabulary there where that it's giving you a chance. What does parallel mean? What does congruent mean? Let me share another use of Geoboards that I often like to do. So there's one of them, I call it a Geoboard riddle. Ask them to come up with a shape that matches that description. Sometimes I like to do what I call possible or impossible. Give them a series of different ones and tell them some of those are possible to make with your Geoboard. Some of them are not possible to make with your Geoboard. You see if you can figure out which ones you can make, which ones you can't make. Turn them loose, give them time to work on it. I will tell you, if you look at that first one, a triangle with 5 interior pegs, there may be nothing really mathematically significant with that, but it's kind of a fun one for them to try. I will also warn you that sometimes you can't make something on a Geoboard, but you certainly can draw it on a piece of paper. So just know that it sort of works both ways with that. So lots of different possibilities, lots of different things going on with that. So I wanted to share those couple of brief ideas with the Geoboard That tends to be a fairly staple of a manipulative that a lot of classrooms have. It's also one that collects dust, again, because it's that rubber band issue. And again, when I used my Geoboard days, my heart does start beating a little bit faster than on a normal day. But I just have a bunch of little dot paper that if a student accidentally shoots that rubber band, they use the piece of dot paper for that day as well. Again, it's not a lifetime banishment. It's just for that day of itself. And I can always tell on those rubber band days, I do that with my first hour. A kid always shoots a rubber band, accidentally, of course. I calmly walk over, remove it. But then the rest of the day, word has quickly gotten out that Mr. Dykema really did mean it. If your rubber band shoots across the room, you just don't get to use the manipulative for that day, but you don't just get to sit and do nothing. You still have to do all of that work on a piece of paper instead. So I want to say thanks in wrapping up. I know we went through lots of different ideas. I would like to give lots of different ideas and show a variety of uses of manipulatives. If you want a copy of that PowerPoint, I am happy to provide a copy of that PowerPoint. There's my email address. Just tell me you were at the virtual manipulative session or the Brainingcamp session so I know which manipulative to send to you. Anytime you've got questions, feel free to reach out to me. There's my Twitter handle. There's my email address. I am happy to support you however I can. And thanks again for all that you do to help meet the needs of each and every one of your students. And thanks for joining us this afternoon, evening, morning, depending where you're at, and coming with us and joining that journey to help improve mathematics education. And I'll stick around and answer any questions that you might have. You can just throw it in the chat box. But otherwise, thank you again for your time.